Okay, so we got a really fun problem here. I still might be a little sick, by the way, so if I sound weird, that's why. Also, sorry it's kind of late when I'm uploading for a lot of you. I got off work not that long ago. And, well, I post when I can. So, following kind of what we did before, we'll go back and look at the vector questions again. But I think it's good to start looking at some of Newton's second laws. We've talked about it before. And yeah, it's good to do some example problems. So this is a pretty good one. The question's up here. It's number 36 in the book if you're following along. It says a plane that's flying horizontally at a constant speed, v naught, so just writing that down, at a height 8 above the sea, must drop a bundle of supplies, which is that stuff, the crate M, onto a small raft, which is where the guy's at. It says write down Newton's second law for the bundle as it falls from the plane. Assume you can neglect air resistance. I know this is something some of you may not like to hear, but that's going to be the upcoming section. Actually, in Chapter 2, there's a few sections about linear and quadratic air resistance, and I'll post videos just talking about them, and then I'll do example problems, so don't worry. Solve the equations to give the bundle's position in flight as a function of time. B, how far before the raft, measured horizontally, must the pilot drop the bundle if it's to hit the raft? And what is this distance if v naught equals 50 meters per second, the height is 100 meters, and g is about 10 meters per second? And then C, within what time interval, plus or minus delta t, must the pilot drop the bundle if it's to land within plus or minus 10 meters of the raft? Okay, so a lot going on there, but it's actually not bad. I drew just a little coordinate axis so we know y means up and down, x means left and right, and z means into out of the page. And like I said, up and down, up is positive and so is rightward motion. So, okay, cool. Let's start with a free body diagram. Just a look of our crate. Well, the crate, which we're calling just M, is going to experience a weight force exerted by the Earth onto the mass, which is equal to just negative mass times gravity because of the way we defined our coordinate system. And our force, our net force, is going to be equal to our force in the x direction, our force in the y direction, and our force in the z direction. Okay, well, let's talk about the easy parts first. The force in the x direction is equal to the force in the z direction, which is 0. And that's just because there's no force in the x or z components. There's no x or z, well, I should say direction, in the x or z direction. There's no component of force. The only force that the crate is feeling is in the y direction, and that's just gravity. So no force is there. With that in mind, we can think of our net force as being equal to 0, comma, negative mg, comma, 0. So I plug zeros in for x and y, and then for y, I just put our minus mg. Now our force is equal to mass times acceleration. But we also know, if you've watched the lecture videos, that's equal to the second derivative of position. So I can divide everything by m, and what do I get? I get the second time derivative of r is equal to 0 minus g 0. So this vector is our acceleration vector. Well, if we want to go from acceleration to position, we have to take a couple integrals. And let's write this out. So the second time derivative and the x direction is equal to 0. And if we integrate this with respect to time, you'll get r dot x is equal to 0 plus our constant c. Well, what do we know? We know that at t equals 0, our speed, v naught, is just v naught x. So our speed at time equals 0 and the x direction is just our magnitude. So for that reason, we can say r dot x is equal to v naught x. That's our constant of integration. Okay, so now that we know that, honestly, there's nothing there. There's no t function. But if there were, it doesn't matter. That's just, if you had r dot x equals t plus c, you would still get that. Basically, what we get is v naught x is equal to c. So r dot x is equal to c, which is equal to v naught x. Now, r double dot z, if we integrate that, then we get r dot z equals 0 plus c, and at t equals 0, v naught z equals 0. There's no velocity in the z direction. So 0 equals c, or r dot z equals 0. And then the last one, if we look in the y direction, this isn't too bad. We get r dot y is equal to minus gt plus c. Now, at t equals 0, v naught y is equal to 0. So r dot y is just minus gt. And if you want to know what I'm doing here, I'm saying our velocity in the y direction is 0, so that's this part, equals minus g times 0 plus c, c equals 0. So we can just conclude r dot y is equal to minus gt. Now, why is v naught y 0? So initially, the plane is moving just horizontally. So all our velocity is in the x direction. So initially for the box, that's all it's going to feel. Just the velocity in the x direction. So for that reason, we say the only initial velocity, when we look at v naught, this v naught's basically, that's the time where we start actually measuring our experiment. So we know right when we start measuring at time equals 0, all the velocities in the x direction, because that was what was given in the question. So hopefully you guys are okay with that. So our r vector, we can now say, is v naught x minus gt 0, which v naught x, that's just v naught, right? Because just as we said before, all the velocity is in the x direction. I'm also being kind of loose with my arrows over vectors, but let's just go with it. Okay, well, we can follow a similar step here. R dot in the x direction is equal to v naught. And if we integrate it, we find that r in the x direction is just v naught t. We can do the same thing in the y direction. Then you get ry equals minus 1/2 gt squared plus y naught, but we said our initial height, we're just calling h. And real quick, just to get it out of the way, there's nothing going on in the z direction. There's really not even a point of looking at it, to be honest. Okay, so just so we're all right with everything, all we did was for the first one, we just integrated both sides to get our position, which is v naught t plus c. And then as long as we let our initial position be at the plane, what we would get is Vx or Rx is equal to v naught t plus c, and at t equals 0, x equals 0. In other words, 0 equals c. That takes care of your constant. If we think of the origin as being lined up with the plane, it's not lined up in the picture, but if you could imagine the plane is right above that orange dot, that's kind of what we're working at. And then for the y, it's the same thing. The only difference is you get r sub y equals 1/2 gt squared plus c, and at t equals 0, ry equals, we called h, so h equals c. So this constant of integration just turns into h. So our position function, r, is equal to our x, which we said was v naught t, our y, which is minus 1/2 gt squared plus h, and then 0 for the z direction. There you go. So that's our position. That's part A. So part A wanted us to write down Newton's second law and then solve the equation to find the position as a function of time. This is r as a function of time. The only variable here is time. So good, we did that. For part B, it says, how far before the raft, measured horizontally, must the pilot drop the bundle if it's not to hit the raft? What is the distance if v naught is 50 meters per second, h is 100, and g is 10 meters per second? Okay, so we want the height to be 0. We want it to hit the ground. And the y portion is our height. So 1/2 gt squared plus h must equal 0. Or 1/2 gt squared equals h. T equals 2h divided by g square root. So that's the time. Now we want to know, not the time, I think I want to know the distance, how far. So if we want to know how far that needs to go, well, we're looking horizontally, so that's just our x component. So we would say v naught times t. So v naught times the t we just solved, square root of 2 times h divided by g, which is, we said 50 meters per second times the square root of 2 times 100 meters all over 10 meters per second squared. which is 50 square root of 200 over 10, or 20. Forgot my units. Okay, so what's our units? Let's see, we have meters times second squared over meters, so that's second squared. This is going to be really good because the second squared, or square root of second squared, is just seconds, and that'll drop, leaving us with just meters. If you plug this in your calculator, you get 223.61 meters about. Okay. And they wanted to know how far before the raft must the pilot drop to hit the raft. So the pilot needs to be 223.61 meters away from the raft before letting go. So this is part B. And then for part C, what does it want to know? It wants to know if we want the care package to be within 10 meters of the raft, what's our margin of error? So x equals v naught t. But if we think of this as time intervals, then delta x equals v naught delta t, where delta t is equal to delta x over v naught. So we wanted it to be within plus or minus 10 meters over the 50 meters per second. So what this is saying, if we look back at our picture, we could be 10 meters behind. So maybe this is, if we think of a coordinate system here, maybe this is minus 10 meters. Maybe this is plus 10 meters. We want to be within that margin. And all we have to do, if you plug this in, you'll get 1/5. So delta t is about 0.2 seconds. For our units, that's meters times seconds over meters. So the units make sense. So the pilot is going to have to be very, very quick. He doesn't have a lot of room for error if he wants the care package to come close. So hopefully this problem made sense. I try to explain it pretty deeply, even with the integrals and our constants of integration. I wanted to make sure there's no flaws in our logic. So hopefully that makes sense, and if not, maybe I can do something else to try to